Hey, what's going on, guys? WukongJS here. In this video, I'd like to share my recent insights regarding the principal variation move ordering that helps to optimize your alpha beta search. Not very significantly, but quite pretty nicely still. So, despite the fact that I've been using this principal variation move ordering in my previous engines and projects, still, I didn't really have that clear understanding that I have now. And that's the reason why I want to emphasize this particular topic and to provide an examples of how in particular the, I don't know how to call it, the most stable implementation kind of looks like. And quite pretty interesting thing that the current implementation I have is exactly the same implementation that is used in TSCP chess engine, but that's not because of just stolen that from that engine, but because I swear I came up with this sort of a technique on my own when I realized the actual logic behind this move ordering. Because I will highlight the mistakes that I was doing before, just to give an idea why now in particular this is so important and why this works. So let's go for some sort of a demonstration of what the principal variation move ordering is. Then we'll quickly walk through the current particular implementation, and then I will describe some pitfalls that I got into before in my previous experience. So without further ado, let's actually start. So if we just make a move and the engine responds back, makes a move in response, these kind of moves are known as principal variation line. PV line for short. So PV stands for principal variation. And the idea of the principal variation move ordering is very simple. We just simply want to, we could have assumed that if we found a principal variation move in the lower depth, it might get reused in the deeper depth. It's not always like that, like in this case in particular. So we started with a move like G8 to F6, and then we switch to this D7 to D5, and depending on the time control used and depending on different circumstances, like how many processes are running on my laptop, if I don't have my video recording software being activated, the move would be different because it takes it has a bit more processing power to calculate, hence it doesn't drop too early. So without this video recording software, it would be like most likely E7, E5 instead of D7, D5, and so on. But it's not the point really. The idea is, so again, like for those of you who's not aware of what is the iterative dependent is, I would rather explain that first to give you an idea why the principal variation move ordering is so important and how to make use of it. So let's say, well, here we were searching for a current amount of time, 1 second. So let's better try to search for a fixed depth. So let's say I want to search, sorry, not like this. I just used the API of my engine. So engine.search, and let's search to 5 ply depth here. Okay, and we have the move B1 to C3, so this is the initial move to make. And please note that we didn't search for depth 5 instantly, so we didn't go instantly here. But first we searched for depth 1, then depth 2, depth 3, depth 4, and then eventually depth 5. So this is what is known as the iterative deepening. So we're iterating the current depth +1 every time, and every time we're making a new search. And you might wonder why this is needed, and actually timing is one of the main reasons for using this. So let's say we're at the depth 4 and time is up. So instead of searching further on, we just return the best move from the principal variation being collected at the depth 4. So that's how it works. That's one of the main reasons to use this principal variation. But the main reasons to use the iterative deepening. But some sort of a side effect of this iterative deepening is that we can reuse the best move from the previous iteration to be sorted first in the next iteration. And by fact, it kind of like helps us to slice some nodes from the search, so kind of like optimizing the search. I will demonstrate how exactly this kind of looks like. Probably I will do this first to give you a visual example of why this is actually better compared to one actually not doing this. And then we'll probably go for I'll demonstrate the implementation and how the things work. So first of all, let me disable, so just want to disable the sort PV move in particular. So I'm sorting principal variation move in both in my Nigamax search and the quiescent search. So let's disable them in both. So I'm disabling this in the quiescent search and also in the Nigamax search. Now I need to update. Yeah, I just forgot what was the number. It was for about 37. Well, okay, anyway, let's try to make the search again. And we have this 38568. And if we just re-enable this back, then we have save. So remember this number, 38568. And when we enable our principal variation move scoring, we have last nodes. So it's not significant, but quite pretty interesting. Now, if we go for depth, let's say 6, the difference would be more significant. So here we have 154889. Okay, and this this number is assuming that we have the enabled move sorting. So if we disable the move sorting again here, in both in quiescence and in the Nigamax search, and update this stuff and try to go for depth 6. So that was 1000. Yeah, and now it's 165. So it was only like, okay, remember this number. So I will now re-enable my search just to give you an idea that the deeper we go, the more significant the difference is. So 165,086. And now let's go for depth 6 again. And oh, hold on a sec. 168. Hold on a sec. Okay guys, just something can run with my browser apparently. So I've just tested this both 7 and 8 nodes and the results are different. So let's go for a test again. I'm sorry for this inconvenience. So again, like let's start. So I just disable my sorting PV in quiescence and in Nigamax search. Okay, I need to make sure to update, and let's go for depth 7. So now we're going to search without the principal variation move ordering. So let's go for it. Okay, and the number is 1,267,778. So 1,267,000. And now if we just enable this principal variation move scoring in quiescence and in here as well, and now I need to update. Yeah, I just forgot to update and run this again. So it was 1,206,000 and so on, and now it's 1,204,000. So it's kind of like how many? Yeah, it's kind of less now. And if we go to depth 8, that takes time, but the difference in nodes would be even more significant. So let's try to command out this sort move and update and go into depth 8. I would rather use my calculator to say the exact difference because I'm very bad at calculating numbers in my head. Okay, so now it takes a little bit of a time because the engine is not really optimized that yet, so it takes ages to complete the depth 8, but anyway, it's not the point. So now as soon as we see the difference in the nodes being saved, then we'll go for the implementation to see how in particular this is working. It's one of the most basic move sorting techniques, and well, I think that every engine actually kind of makes use of this sort of a technique. Okay, it really takes ages, but it's really worth of seeing. Okay, finally we get the result. So let's save this in the calculator to make sure that we don't miss the numbers. So we have 8 millions, 27. Okay, sorry. I want to go to, let's go to the basic mode. So 8,279,597. Okay. 8,279,597 minus, and now we enable the principal variation move sorting back in quiescence and in the Nigamex search again. So don't forget to update, otherwise it won't be valid. It would be just from the previous iteration. And also you need to make sure that in the network you have this disable cache. Oh my god, I forgot how this view control element is called. This guy. Okay, so you need to enable this button. Let's call it button. Otherwise, your JavaScript may be pre-cached and the results would be the same every next time. So again, like this last number is not for depth 7, it's not to 6, and it's only 1 to 4. And let's see the difference at the depth 8. So it would now be, it's just hopefully after ages pass, it should get completed. Okay, finally. So we have 1 million less at very least. So this number, so let's just copy this number, and I want to paste this number, and equals. So we have saved. Oh no, it's I said that I'm very bad in calculating big numbers in my head. So it's not 1 million definitely. It's only okay. So this is 488 thousandths. So it's almost 500,000 nodes being saved. Well, it's very roughly, but still. So this is the number. So 488 thousandths to 73. So this is the number of nodes being saved at depth 8. And again, like the deeper we go, the more nodes are getting saved. Obviously, it's not a significant improvement, and you might wonder that it's not worth of it. But again, like for me personally, the matter of principal variation move ordering is just interesting as, I don't know, it's just interesting for me as a technique, as one of the possible search optimization techniques. Because again, like every time I was trying this before, some weird things happened. So I had, it was actually slowing down my search instead of making it faster. And now finally figuring it out how it works, it makes me really happy. So the next step to consider, I just want to so let's go to the sort principal variation move function. So where is the function call itself? Sort PV, it's right over in here. And here I just want to say console.log, and I want to print the move, the particular current given move that is being sorted. So move to sort. Let's even call it a principal variation move to sort, and we use this one copy. But if we want to make it in a string format, we need to say move to string first, and then like this. And if I now just update my stuff, and let's search for, let's depth 6 would be literally enough here. And now we can already see the following steps. So after searching that for depth of 1, we have the only principal variation move, and we match it here. Then we have 2 moves, and we match every of these moves. So this means that every time the ply we're searching at contains the move that is considered to be the principal variation move from the previous iteration, that means that we need to sort it first before all the other moves. Because the general order for the move ordering, how it works, so first we sort captures in so-called most valuable victim, less valuable attacker. order which gives the most significant, the Titanic, just absolutely I don't know, like the most. It does the most of the job, because without that, I was mentioning that in one of my previous videos. So without sorting captures, your engine would be doomed to be at a depth of 1, assuming the question search looking for a composition recursively. So in positions where many captures occur, it's literally impossible to get out of the depth 1. But with this capture ordering, we can go to even depth 6, depth 7, 8 at the moment. So that's one of the most significant factors, basically. But here we do match this principal variation move, and it means, like, let's say just want to visually explain this. So we've collected this B1 to C3 move. So when we come to the depth 2, we want to sort move B1 to C3 first, and then calculate further on. It doesn't obviously mean always that the principal variation won't change like it happens here, but it means that when it comes to, well, actually it tried this D2 to D4, yeah, and then it dropped back to this B1 to C3, B1 to C3. So yeah, the principal variation is changing, but the idea is, if we do follow the principal variation, well, let's say like here after depth of 2, we have 2 principal variation nodes. So let's say he found a better move, but then he orders this move first, and eventually it happens that it's about to be best. It might not be like that, but it's just a matter of the move ordering to slice some nodes from the search. So I just want to say that every time we so here we have the like ply 0, ply 1, ply 2, and if at the current given ply we're having the move in the principal variation, we just order it first, and probably it would be a little bit easier to understand within the code. So here is how. So I will drop the explanation of follow PV flag, which is absolutely essential. But for now, I just want to emphasize the logic itself. So before, so this sorted PV, it happens in both quiescence and Nigamax search, just right before we do the loop over the moves in the move list, before this sort of a loop. Maybe I should have provided the commentaries. Loop over moves. Yeah, maybe that's a good idea. Loop over moves. And before the actual loop over moves, we do this little loop over all the moves. So it's the loop is literally the same, but and it might seem that it takes time, but it's worth of it, obviously, because we slice some nodes. So here, for every single move, we just if the move equals to the move that we have in the principal variation indexed by the current search ply, that means that the current move we're dealing with. So this is the list of the generated moves of just generated moves. So in case if we have this move equal to the move at the same search ply in the principal variation table, that means that we're now following the principal variation line, and we're setting this flag as well, but that's not the point now. And we want to score it the most, so we score 10,000 for captures plus MVVLV value, which stands for most valuable victim, less valuable attacker, then killer moves, then history moves, but that's the different topic. So we want to score the principal variation move first above all the other moves, so to make sure it would be searched first, because we assume that it's kind of the best move. And even though it's not, might always be like that, still, as you've seen here in this particular example, it actually makes search it makes some node slicing from the search, which makes search a little bit faster. So now one of the most essential parts, this follow PV flag, because I was trying this match many times before, but I didn't understand completely how this follow PV flag works, and without this understanding, eventually I had much worse results compared to the correct results where you actually need to slice some nodes. So let's just get rid of this command line here, and let's make sure that we're no longer, printing anything. So let's try to understand how this follow PV works. So this is the global variable, basically is declared on top of search. Here it is. I'm not sure whether it gets resetted. Yeah, that's the good question. So should I reset that? Well, okay, let's go to the very first occurrence of this follow PV we find in the iterative deepening framework. So we're setting it to true here. Yeah, probably that's just, yeah, you know, like when you're making videos, some questions arising that you never ever think of if you don't come back. Yeah, so now I'm just thinking, should I actually reset this? Well, probably I don't, but that's just another thing to think about. Well, let's forget that. So every time we start in, so here is the iterative deepening framework. So we're calling our nigamax search function for depth 1, depth 2, and up to depth that we are getting from our search position. Doesn't matter if it's the fixed depth search or if it's fixed time control search. Still, we would be iterating over like from 1 to depth 1, depth 2, depth 3, and so on. And every time before we call our nigamax search, we need to make sure that we set this follow PV flag equals to 1. Okay, and then when this follow PV actually fires, so sort PV move, yeah, here. So we come into this code only in the case if the follow PV flags is equal to 1, which we just set to 1, so it's true. So we need to check out whether whether principal variation move is available. So by default, we reset this. So we assume that we don't actually match a principal variation move, and this is the core part of the entire algorithm. So we need to reset it every time we're in. But then, when we loop over the moves, and surprisingly we find a move that is available in the principal variation, that most likely means that the next one, at the next search ply, would also be the principal variation move. We just need to wait until the search ply would increase. So literally we kind of make a move, and then we just make a response. So for that response, we need to make sure that whether that response relies within the principal variation table or not. So that's the idea. So every time when we hit the actual principal variation move, we reset the follow PV flag back to 1. Okay, and when the next time we come to this sort PV, again, like we get in here, and again we reset it, and this happens until we kind of like find another move in the principal variation. So not only we're not only sorting, say, this one, but we're also sorting this one and this one and this one eventually. I don't know, probably my explanation sound weird. I'm sorry for that, but that's again, like, if you could ever realize how bad my understanding of sorting principal variation was before, you would truly believe that now I can understand at least something about this sort of a technique. Yeah, so that's how it works. And this explains another thing that was a complete mystery to me regarding the implementation of principal variation move over in TSCP chess engine, which, well, actually, yeah, you might wonder that I've just stolen this code from TSCP, but I swear I understand how this works now, believe it or not. So the reason why I was wondering, like, why the heck TSCP was storing the principal variation move. So we also need to store the principal variation move in order to match it later on. And also storing principal variation moves is good in order to just output the principal variation line. So I was wondering, like, why the heck to store the principal variation move within the quiescent search. Let me just find this. Yeah, store principal variation move. So every time we hit the principal variation move, again, like, remember, in alpha beta search we have 3 types of moves. We have so-called fail high nodes. Fail high. Where is the beta? Here, beta. Fail high nodes, those nodes is known as fail high in case if the score is greater or equals than beta, which produces so-called beta cutoff. We also have the fail low nodes, those nodes that do not increase the alpha, which in alpha beta serves as the best score basically. And again, like assuming the fail sub framework, we don't have a situation where when the score can exceed the alpha beta bounds. If it does exceed, it calls fail hard framework. If it does exceed, it calls fail soft framework. So we're within the fail hard framework, where when the best score doesn't exceed the bounds of alpha and beta. So in this case, we can say that alpha kind of is the same that the best score. And okay, so 3 types of nodes. So fail high node, fail low node here, and principal variation node every time when the current given score taken from this recursive call actually is better than the current alpha. In this case, if we have this principal variation move, we just write this to the principal variation table. That's how it works. So I was wondering, like, why the heck to write this principal variation move within the question search? And it turned out that actually sorting principal variation move in the question search does increase the number of sliced nodes, the eventual number of the sliced nodes. So if we don't sort this, it just gets less nodes sliced. So I was just thinking, like, we don't really want to show the principal variation on the question search because it's kind of like goes beyond our interest, because we're only interested in the variation of the either fixed depth or time within the main enigma extraction. This question only serves the purpose of getting rid of the horizon effect, just to avoid engine giving pieces away. But at the same time, surprisingly, it happens that actually storing principal variation move and then sorting them within the question search actually helps improve our search a little bit. It's not significant, but anyway, like from the perspective of understanding how in particular this alpha beta search works, it might be interesting. And interesting fact that not all the engines actually using this, and it might happen that one day I will drop this in my WukongJS engine as well, but at the moment this was so insightful for me, guys, so I just wanted to share this sort of a idea with you, like trying to explain how this sorting of principal variation moves actually works in a chess engine. Well, this is it from my side. Not sure whether you've enjoyed the video, found it useful, but at least I've enjoyed the fact making it, and even more I've enjoyed the fact of finally maybe not having the complete understanding of how it works, but at least at the moment I think that I feel like that I understand it completely on how it works. So again, like for me personally, chess programming is the matter of fighting my own stupidity. So from this perspective, I think this is really good thing. Okay guys, so this is it from my side. Until the next time, and take care.